So what we're going to talk about here is the normal model. So we're going to see what the normal model is, this bell-shaped curve. These bell-shaped curves come from a continuous distribution. So with the binomial model and the discrete random variables, all we had were discrete cases. There were only certain values for the outcomes. With the continuous distribution, what we're going to see is if this is our number line here, we can land anywhere. We can land at weird decimal places, and that's okay here. So that's what's going to make this kind of smoother curve, is that there's infinitely many possibilities along this number line here. What defines our distribution is defined by a mean and a standard deviation. So our notation here, we're going to have some population mean and population standard deviation describing the behavior of our data. So if we have this random variable x, how we would define it is with the normal model, and that's what this capital N is going to say. And whenever you see the word normal, or this kind of defined by in this capital N, I want you to immediately think about a bell-shaped curve. That's what we're describing with that word normal, or this capital N. And then the information that the normal model needs is a mean and a standard deviation. So those two pieces of information, the mean tells us the center. It's where we expect to be most often, so that's going to be where our peak is. So right in the middle is going to be our mean. And then our standard deviation is going to tell us how our data deviates, how we expect to go above and below our distribution. So actually, if we drop down to the drawing that we have down here, if this is some normal model with some mean and some standard deviation, how this is divvied up right now, if we know our mean, that's what goes right in the middle here. So that would be whatever our value for the mean is. Then how this number line separates right here is by standard deviations. So this cutoff point right here is coming from taking our mean and adding on one standard deviation. And then this next one would come from taking our mean and adding on two standard deviations. And with this, let's even go one further to where we would add 3 standard deviations. So we can get this number line out by moving up by standard deviations, and then this other direction by moving down by standard deviations, taking our mean minus 1 standard deviation, our mean minus 2 standard deviations, our mean minus 3 standard deviations. So this is how we're going to get a number line out for our bell-shaped curve. So if we look at our example up above here with the rainfall in Portland, they tell us we have this mean of 40, standard deviation of 8, and we want to label the model here. So this right here, again, that 40 is our mean, standard deviation of 8. So this is saying if we have some rainfall in Portland, it distributes by a bell-shaped curve centered at 40 with a spread of 8. So 40 goes right in the middle, and then moving to the right, we add by units of 8. So if we add 8, we'll have 48. Add on another 8, we'll have 6. Add on another 8, we'll have 64. If we subtract 8, we'll have a 32. Subtract 8 again, we'll have a 24. Subtract 8 again, we'll have a 16. What we get is this number line, and then we can see where we have these higher peaks, that means there's a higher probability of occurring. So where 40 is our mean, it's that we really expect to have rainfall at 40, or at least really close by to 40. Between 32 and 48 inches for Portland is common annual rainfall. But then as we get further away from the center, as we go into these tails, that brings through the idea of smaller probabilities. Like to have rainfall of 64 inches in a year, incredibly uncommon from the middle. So that's where these two numbers work really well together. We get an idea of where we expect to land, but then also how the numbers distribute to what's likely and what isn't likely. So you can see these values out here in the tails are very unlikely outcomes. As we get closer to the center, this is where we expect to land. Some things that come through with these bell-shaped curves. if we have a bell-shaped curve, the total area under the curve is 1. And what this brings through is the idea of probability. There's a 100% chance of landing under this curve, which is basically saying, given all the possible number of annual rainfall values, there's a 100% chance Portland had something occur. But then what we're going to end up doing is, given this bell-shaped curve, we can find certain areas. We can talk about like the probability between 32 and 40 inches of rain for Portland. And what we end up doing is shading that area, and we calculate this area, and the areas for this represent probabilities. So if we went through this process of calculating the area that's between those two values, it would be describing the probability of 32 to 40 inches of annual rainfall for Portland. So this is how we're going to link to probability with these bell shapes. So, with these areas, what we're going to have is something called the empirical rule, which is kind of a quick rule of thumb if we're landing nicely on these standard deviations away from the mean. And with that, we can use the empirical rule. What we're going to see is eventually that often we're not landing perfectly on these values, and that's where we're going to switch over to GeoGebra, and GeoGebra will help calculate some of these values. So our empirical rule. Our empirical rule says that 68% of values fall within 1 standard deviation of the mean. Meaning if we go 1 standard deviation below to 1 standard deviation above, this will cover about 68% of the data. So 68% chance of landing between those two values. Between 2 standard deviations away, if we go from here all the way up to here, that's about 95% chance. And notice that these are estimates. When we use GeoGebra, we can get a more exact value out, but quick rule of thumb estimate would say 95% of the data is between there. And then 3 standard deviations away, all the way out here to all the way out there, it's going to cover about 99.7% of the data. So with this, we get an idea of how the probabilities distribute. A rule of thumb that we use too, another rule of thumb, would be that any values more deviations away from the mean are considered unusual. Meaning, if a value is more than 2 standard deviations away from the mean, which would mean it lands out here or out here, then there's only about 5% of that occurring, which is so unlikely. So it'd be if we go back to the rainfall, if we had an annual rainfall of 58 inches, because that's landing more than 2 standard deviations away, that would be considered an unusual result. That's a very unlikely result. And the further you get away, kind of the more extraordinary it becomes. But if we had annual rainfall of, say, 50 inches, that's within the 2 standard deviations away. That's not that extraordinary. That's kind of expected. It's a little above average, but close enough by. Drawing these bell-shaped curves, so here we have these kind of number lines ticked off for us, but let's see what makes this 1 standard deviation away. Such that if I am just drawing a curve by hand, and I draw my bell-shaped curve, it's easy enough to start with the center of the graph, but then how do I know where 1 standard deviation is? Is it here, or out here, or right there? And what you want to notice is the curvature of the graphs, and there's something called concavity. Concave up occurs with our parabolas, and it's where we have this shape here, kind of opening upward, and then concave down is where it opens word. And what we can see with our graph, if we just look at half of it, we have two concavities occurring. We have concave up over here, and at some point it switches to concave down. So if we imagine kind of following our concave up scenario here, if I imagine fitting a parabola here and then continued fitting it, eventually it's going to depart from the graph. And if I did that with the concave down part and kind of followed it until it departs in the graph, it's this point where it switches. It's called an inflection point. Wherever it flips, that's one standard deviation away. So if you're drawing by hand, what you want to do is kind of visualize this changing point. Here we have concave up, here we have concave down. So about right there it's switching, which then can give me my 1 unit away for one standard deviation. And then once you have that distance, you just kind of follow that distance to make your number line. And same thing on the other side. Just use that distance and you basically create a ruler once you figure out one standard deviation away. So that's how you can make a sketch by hand, which I highly recommend doing for every single scenario. Having a sketch is going to really help out with these problems, and then when we're working with these probabilities that land on certain standard deviations, we can use this empirical rule. It's going to be what we use in this next example.